Kepler and Newton. The German mathematician and astronomer Johannes Kepler studied data on planetary motion that had been carefully collected over a 20-year period by the Dane Tycho Brahe. Brahe was a very colourful character, and if you ever get time, it's well worth finding out something about his life. Kepler came up with 3 mathematical laws that describe the motion of the planets. The first was that the orbit of each planet is an ellipse with the Sun at one focus. The second, a line joining the planet to the Sun, sweeps out equal areas in equal intervals of time. And the third, the square of the orbital period of a planet is directly proportional to the cube of the radius of orbit, which we can write like this. The time period squared is directly proportional to the radius cubed. He could give no reason for these laws other than that they matched observations. They're what are called empirical laws. They're based on experiment rather than any theory. Newton's universal law of gravitation and his second law of motion explain why Kepler's third law is observed. You need to be able to use these 2 laws to derive an expression which includes Kepler's third law. The planets are held in orbit by the gravitational attraction between themselves and the Sun, and the mass of the Sun is much greater than the mass of any of the planets, and so it's a reasonable assumption that the Sun remains stationary as the planet orbits it. The gravitational force of attraction from the Sun provides the centripetal force needed to keep the planet in orbit. Newton's universal law of gravitation tells us that the force F is equal to the gravitational constant g multiplied by the mass of the planet and the mass of the Sun divided by the separation of their centres of mass squared. Newton's second law tells us that the centripetal force F is equal to the mass of the planet multiplied by its speed squared divided by the radius of orbit. The gravitational force provides this centripetal force, and so we can combine the 2 to get this expression. Cancelling the m's and one of the r's gives this, but the speed of the planet is simply the distance it travels over the time taken, which is the circumference of its orbit, 2 pi r, over its time period t. We can substitute this expression for v here to give this, which we can now rearrange as t squared is equal to 4 pi squared over gm times r cubed. All the terms here are constants, so we see that time period squared is equal to a constant multiplied by the radius of orbit cubed, or time period squared is directly proportional to radius cubed, which is Kepler's third law.